Yep, you're good to go.
Excellent. So again, thank you very much for the introduction, and good afternoon. As the title of the talk suggests, this is a talk on subduction trenches, but my regular stomping grounds are the waters round about the UK and the Northeast Atlantic. But in the last 7 years or so, I've been lucky enough to participate on a number of projects exploring the deepest reaches of our planet, including subduction zones and mid-oceanic ridges. So since 2015, I think I've done eight or nine expeditions to these ultra deep areas. And on the back of some of that experience and working in these environments, I was lucky enough to be expedition geologist for the 5 Deeps expedition, which will crop up later in my talk today. But I'm going to take you on a whistle-stop tour of a couple of the deepest reaches of our planet. A quick introduction before cherry picking a few research highlights along the way. But please sit back and I hope you enjoy the journey, and all things going well, there'll be time for the questions at the end. So it's worth taking a really brief step back in time to ponder the fact that it wasn't until the 1950s that Hazen and Tharp partnership started publishing maps of the ocean floor topography. So the partnership began using photographic data to locate downed aircraft from World War II, and later began to map the topography of the oceans. So Bruce Hazen went offshore collecting the data, and Marie Tharp worked back in the office producing the maps. Sort of back in the day, at that time, women weren't allowed to go offshore, and she didn't actually go offshore until 1965. So the first map was produced in 1957 of the North Atlantic, and it was really the first time the complexity of the ocean floor was revealed. And well, it raised an awful lot of questions. What was happening at the big mountain range that goes up the centre of the Atlantic Ocean? Was this where new crust was being created? I mean, it was over 200 years ago that James Hutton came up with the theory of the heat engine, what we now know is the sort of driving force behind the movement of the tectonic plates that make up the Earth's crust. And it was more than 100 years ago that the German scientist Alfred Wegener suggested the idea of continental drift. So this early map, for the first time, seemed to hint at some of these global forces, but it was still being, it was still viewed as controversial at that time. So if we flash forward 20 years and we see the same team produce the very first attempt to systematically map the world's oceans. So this was only in 1977, which in my mind is still quite recent, and that was the very first time that a global bathymetric map had been attempted. So this map contributed towards the general acceptance of plate tectonics, which was, as I said, at that time still a relatively new theory and highly contentious. But this map revealed for the first time a global network of mid-ocean ridges where new crust is being made, subduction zones where crust is being destroyed or recycled, seamount chains, which also give a flavour for the movement of the tectonic plates over time. And even by today's standards, I feel that this is a truly remarkable map still. You can also view this map in Google Earth as a historical layer. So if you've got time and you're sort of cruising around Google Earth, feel free to turn it on. But where are we today? So, I mean, there are a number of global compilations out there, but the best is probably GEBCO, and they release frequent updates. I think there was one just towards the end of last year. But again, you're kind of led into a slightly false sense of achievement. Look, the world's oceans are covered. There's nothing left to query, to look at. But if we look at the detail behind the pretty picture, so you should always question your sources. You can interrogate the data behind the grid that's shown in the map on the left there. So this is the source grid of the GEBCO bathymetric compilation. And at this scale, the world ocean appears much better covered with ship soundings than it actually is, so with real data points. But the fact is that the available data used to compile GEBCO provides a depth control point to only about 18% of all of the grid cells. So in each grid cell is about 1,000 meters by 1,000 meters a kilometer across. So, so much of the water depth information is derived, instead of from ship soundings, it's derived from satellite data rather than acoustic surveys. And so as a result of that, just from the different techniques used to acquire the data, there's quite a lot of variation in the resolution of the mapping of the seafloor. So differences in techniques, but also the collation of information spanning really long timescales. You know, we've got some really old data sets in GEBCO, but I mean, actually, that's the best data that we have for some of those areas. So that's not to sort of take any credit away from those. So if we look a little bit more, these are the high resolution multibeam lines that are available globally. And yeah, the sort of just sheer size of the ocean makes making a complete high resolution up-to-date map a long way off. But, you know, I suppose it's sort of reasonable to assume that we've got a broad understanding of what the morphology of the ocean floor is. But just to sort of reiterate that, you know, only 18 to 20% of the ocean actually have a depth control point. The rest of it is made up of satellite derived data. And I'll keep coming back to this point throughout the presentation today. So that being said, it might seem that I've been quite disparaging of global or regional data, predominantly derived from satellites as a tool for research. But far from it. We've recently had a study published that has used these sort of broad scale regional data sets. So we can look at the broad seascape and work across disciplines to explore some interesting questions. So the deepest parts of our ocean, the region between 6,000 and 11,000 meters depth, is known as the Hadal zone, and it represents some of the most active and diverse habitat on Earth, in my opinion, obviously. But understanding the extent of the Hadal ecosystem is difficult due to the complexity of the seafloor topography or geomorphology. So traditionally, biological studies of Hadal species and ecosystems has focused on the really conspicuous subduction zones. But these form quite sort of fragmented, isolated, sort of inverted islands, if you will. So at great depths, sort of these depths exceeding 6,000 meters, the presence of features such as, you know, fracture zones and basins which exist in the middle of these tectonic plates become more important. But, you know, traditionally they've been overlooked in sort of traditional sort of Hadal studies. So just to sort of look through an example from the Northwest Pacific Ocean. So there's an awful lot of Hadal features. So there's an awful lot of water depths that exceed 6,000 meters in this area. And just from a sort of basic sort of high level question, you know, what is the true extent of this sort of deepest marine ecosystem? And can we use global data sets to have a look at that? So you can see straight away that there's obvious subduction zones. You know, there's the Palau, Yap, Mariana, Volcano, Japan, and so on. And just employing some basic morphological mapping, we can start to calculate the Hadal areas of these subduction trenches. And that equates to about sort of 686,000 kilometers square. Now, the global sort of picture of Hadal zones that was often sort of cited was once thought to only cover about 800,000 kilometers square. So you can even sort of see already that in just this one sort of geographic region in one ocean, we've almost met that often cited figure. So that figure of 800,000 kilometers is the total Hadal ecosystem globally, is already looking like a vast underestimate. But if we look a bit deeper at the data set in the area, we discover that if you start to look at the basins that exceed 6,000 meters water depth, fracture zones, which form perpendicular to mid-ocean ridges, if you start to look at the data, you can see that these sort of smaller sort of Hadal ecosystems are spotted all across the ocean plates. and that increases the total Hadal ecosystem area potentially 4 times, so just under 3 million square kilometres. It's a hell of a lot larger than, you know, if you only look at and you only target subduction trenches alone. So if we sort of look a little bit deeper at some of the sort of individual components of the Northwest Pacific, if you look at the Mariana Trench, it was once thought to be one continuous Hadal habitat. So the regional data reveal that the Mariana Trench is in fact 5 isolated areas, with the most northern being what the Russian scientists call the volcano trench in the far north there. And this is important as one of the main characteristics of Hadal ecosystems is the high degree of species endemism. So that's sort of species that have evolved and they're only found in these sort of deep water depths exceeding 6,000 meters. And it's thought to be a result of sort of physical isolation driven by the complex topography of the seafloor, increased seismic activity compared to the surrounding abyssal plains, increased hydrostatic pressure and reduced food supply. So there's an awful lot of different elements that are contributing to endemism in the Hadal environment. In the most recent studies, the 2 main organisms that have been used to study endemism have been amphipods and fish. And amphipods are typically collected in sort of large numbers, consistently in large numbers using baited traps, while the fish are more often observed on camera data, so they're not all that easy to catch a physical specimen of. But current theories are suggesting that most amphipods form isolated populations that can't readily cross abyssal partitions. And with a few rare exceptions, this is also believed to be the case for dominant fish species sampled from depths exceeding 600 meters. So the Mariana Trench, it's not just one Hadal habitat, it's 5. But then we look at the sort of broader Aizu, Bonin, Japan, Kuril, Kamchatka trenches. Just using the broad scale data, we can see that these form one continuous Hadal habitat. So one continuous corridor for specially adapted Hadal species to travel from offshore Russia to offshore the Northern Mariana Islands. So there's no biologically significant sort of shallow water divides between these 3 trenches. They're all joined, and that means that gene flow can readily occur. So what are we looking at? We can see that the Hadal ecosystem, just sort of from a broad perspective, is much, much larger than we previously thought, and that the sort of shape of the seafloor, the geomorphology, is crucial in understanding the distribution and genetic connectivity of these sort of specialist Hadal species that inhabit these really great depths. So the upshot is that traditional studies into sort of Hadal environments and ecosystems shouldn't really just concentrate on subduction zones alone. You know, they need to take into account these sort of more discrete, sort of smaller stepping stones, because they're going to be significant when you start to think about connectivity studies and stuff. So there's quite a bit that we can start to unpick with a regional perspective, but what do we start to see when we start looking in more and more detail? So the devil is in the detail, and I'll just take you through a few aspects of the 5 Deeps expedition that I mentioned in the introduction. That was conceived and financed by Victor Vescovo, a sort of American explorer who came up with the idea to find and dive in a submarine to the 5 deepest points in the 5 oceans. So we got involved and we started to look, well, just do we know where the 5 deepest points are? Looking at the available published bathymetric data and maps and old records from ships spanning the sort of 19th, 20th, 21st centuries. You know, we came across issues not just with naming conventions and all sorts, but just resolution of data. And surprisingly, you know, in some places it was really bad. Areas like the Pacific and Atlantic are pretty well surveyed, and the deepest points are pretty well known. But in other areas, such as the Pacific, the deepest point on Earth for a long time was thought to be in the Tonga Trench, and recorded depths for the Mariana Trench and the Tonga Trench are actually pretty close. They're almost within the error margin of the equipment, the multi-beam echo sounders that we'd use to survey these areas. And the Indian Ocean, for example, the deepest point in the Indian Ocean could be in the Java Trench, or it could be in the Diamantina Fracture Zone. And again, the sort of published depths for these features were very, very close within the error margin of these of the systems that we use to survey. So yeah, it was interesting sort of planning where Victor should target and go in his submarine, but his issue was that there wasn't actually a submarine available to get to the bottom of the ocean and back. So the first manned descent to the deepest point on Earth was back in 59, sorry, using the bathyscaphe Trieste. Walsh and Picard took almost 5 hours to descend down in the Trieste. It was a strictly sort of up and down maneuver. They didn't have the ability to sort of do a transect across the seabed. So they spent about 20 minutes on the seafloor making some observations, and then they released their weights and came back up in just over 3 hours. So it was pretty snug in there as well. But nowadays we use syntactic foam, which supersedes sort of gasoline-filled tanks for flotation that was used back in the sort of Trieste days. But nowadays, if we sort of look at sort of modern technology, since Don Walsh and Jacques Picard went down in 1959, only ROVs had made it to Challenge Deep until the March 2012, when James Cameron built and piloted the Deep Sea Challenger submersible. And the shape of that submarine was very different to the Trieste, and its shape was designed to go up and down through the water column very quickly. He only took just over 2.5 hours to reach full ocean depth, and he used his time down there, almost 3 hours on the seafloor, to undertake a number of transects of the seafloor, making observations, which he went on to publish. And there's the reference down in the bottom right-hand corner there. So unfortunately, the Deep Sea Challenger was lost. It caught fire on its way to Woods Hole. So it was lost to science and deep sea exploration. So Victor had to look at commissioning and building his own submarine. He worked with Triton submarines to do that. I won't go into too much detail here, but there is a short YouTube video. The link is on the top right there, that will go into how they actually made and built the submarine. So I would recommend that you go and have a little look at that. But just super quick, these slides are from John Ramsey, who designed the submarine. But you've got a sort of titanium sphere and a titanium frame on which all your syntactic foam is attached. You've got communications and sonar across the top there, either side of the entrance and exit trunk. You've got your batteries and your weights for allowing you to sink, and then you release your weights to come back up. And just this view sort of shows that it's not quite a teardrop shape, but it is a sort of a lozenge shape, I suppose. And again, much like Deep Sea Challenger, it was made that way so that it could go up and down through the water column very efficiently and quickly. And then it's got the thrusters on the sides there to allow movement along the seafloor and up and over obstacles and features that we might find down there. And there's 4K cameras sort of all over the external part of the submarine, so you can use your cameras as well as the viewports to observe and record your surroundings, your environment. The 5Deeps also had a suite of scientific landers, which could record video, take samples and so on. They were also used for navigation and communications for the submarine. And pertinent to not only this presentation, but my own sort of research generally, is that the vessel that the Five Deeps used was fitted with a EM-124, which was the sort of latest deep water multi-beam system, so that we could actually undertake data acquisition, not only over the deepest points as we were sort of going and doing our missions, but between the points as well. And all of that data is being has been submitted to Seabed 2030, which is an ambitious global initiative to produce a high resolution global bathymetric map. So all of the data that has been acquired in Five Deeps and all of the expeditions since then from carried out on Pressure Drop, the vessel, has been submitted to Seabed 2030. So I won't discuss the entire year-long expedition. I have given sort of lectures on that previously, but I just really wanted to cherry pick a couple of examples which we're working on right now. So this is all sort of current research that we're undertaking at the BGS. And if you're really interested on the data that was acquired in the Five Deeps over the sites of the five deepest places in the five oceans. We've just had the data paper accepted last week, so it should be online imminently. And so keep an eye out for the Geoscience Data Journal for that. I'll probably put it out on Twitter, so if you follow me on Twitter. So first, let's talk about the South Sandwich Trench. So, and as I said, I won't take you on the sort of full Five Deeps sort of experience, but the Southern Ocean, gosh, you can't beat it. Being down south, as they say, is possibly one of the most spectacular places that I've ever worked. And it's just everything you would expect from a documentary series. And you do have to just sort of pinch yourself because it's all just there. You've got penguins, icebergs, whales, while you're working out on deck. It's really quite spectacular. But you're not just here to look at my holiday snaps. So the South Sandwich Trench is a large trench, arcuate-shaped trench spanning the South Atlantic and the Southern Oceans. And it was first discovered in 1926 during the German Atlantic expedition, which took place in 1925 to 27. And they were using this brand new thing called sonar, a new development and really cutting edge for the time. And it was deployed on the German vessel Meteor, which was the world's first to make use of this newfangled technology for scientific applications. So although the South Sandwich Islands themselves had been discovered by sort of Captains Cook and Bellinghausen in 1977 and 1819 respectively, the presence of a sort of a four deep, as it's called, similar to that which was known to occur on other volcanic island arcs, it was only predicted and confirmed in 1926. So the trench itself, it's caused by the subduction of the South American plate beneath the South Sandwich plate, with the South American plate being subducted west at about sort of 65 to 78 millimeters a year. So the trench is deepest in the north and it shallows to the south, where it's bounded by the South Sandwich fracture zone, which is just at the bottom of the map on the right there, SSFZ. So that feature trends sort of east-west and forms the boundary between, well, part of the boundary between the South American and the Antarctic plates. But where my interest came in is that the South Georgia and South Sandwich Isles Marine Protected Area is one of the largest MPAs on Earth. And as part of a review of that MPA, there was a sort of an outcome from that review that highlighted the need to enhance bathymetric knowledge around the region, specifically the deep water zone, the deep water sort of system. There was just a recognition that much more data was needed from the ultra deep sea to support the existing MPA. So the image on the left is the most recent sort of GEBCO 2020 compilation, and you can see that there's basically a lack of detail in the trench floor. The black contour on the right, sort of which opens up like a sort of funnel at the top and narrows towards the bottom, that's the 6,000 meter contour. But it's worth sort of mentioning that the blue lines are the multi-beam lines. The thin blue lines are single beam data sets, but most of the trench is covered by satellite data alone. So even with sort of recent mapping efforts and compilation put together by the British Antarctic Survey and the International Bathymetric Chart of the Southern Ocean, as I say, not much accurate information is known for this trench. So we went out in, oh gosh, February 2019, and we acquired sort of 15,000 kilometres square along the trench axis from south to north. And it's worth noting that only 7 kilometres square of the trench axis had been surveyed before we got there. So as I said, the sort of knowledge about the morphology of the trench was relatively low at that time. So we acquired high resolution data for the entire trench axis, and the deepest point overall is in the Meteor Deep, named after the research vessel that sounded it in 1926 using that early technology. And it's worth noting that they sounded 8,264 meters, and using up-to-date technology, we only refined that by 1 meter. And so I mean that's pretty good going for early sounding accuracy. So I'll whistle through some of this, but using sort of the sort of interpretation that we've undertaken in not just the South Sandwich Trench, but a number of other trenches as well, it's a mixture of automated methods run on the bathymetric dataset and expert interpretation. So we mapped a number of features such as trench floor, ridges, escarpments, slopes, seamounts, submarine landslides, and so on, using sort of the open source toolboxes that you can import into ARC Toolbox, and also the tools that are available within ARC Toolbox generally. So just in the short time we have, cherry picking a couple of features. In the north here, you know, the pale blue outlines and the image on the right, left even, are seamounts, and it's worth noting that we've identified over 100 seamounts in the sort of trench axis area alone. I think previously only 2 had been predicted from the GEBCO data sets. We're already learning new things about the South Sandwich Trench. A number of these seamounts are cut by ridges, which are the sort of seafloor expression of faulting related to the process of subduction. And some of these ridges are sort of, you know, hundreds of meters up to 1,000 meters in height. So I mean, they're truly spectacular features. So if we head down the trench a little bit, we've got an example here of a ridge complex. It's likely part of it's part of the incoming original fabric of the incoming plate, and the complex itself, you know, that I've imaged here with the sort of red and the yellow lines, that's sort of 65 kilometers in length, and it's sort of 1,300 meters high from the trench floor. But the take-home message here is that the escarpments, which are sort of cutting up these ridge complexes, these reflect a sort of bend-related faults, so that it's reflecting the downward flexing of the tectonic plate as it's being forced underneath the sandwich plate to the west. So in total, sort of 640 escarpments and their corresponding crests have been mapped during this project. And just sort of if we hop down to the southern end of the trench, and if we remember from a couple of slides ago, the trench broadly shallows to the south, and if we look at the area where the South Sandwich fracture zone intersects the trench, that's the southern boundary, we can see the clearest impact that the inherent fabric of the incoming plate has on trench morphology. So here we can see the impact of the influence of the incoming fracture zones of there's the Bullard fracture zone, the South Sandwich fracture zone, and these form perpendicular to the South America Antarctic ridge, which is located sort of further east. And as these fracture zones sort of enter the trench axis, they end up sort of forming these sort of confined sedimentary basins, which have got these sort of faults superimposed on top of them. So you end up with these quite distinct basin complexes in the southern end of this trench. Yep, and sort of just a little bit more context that we can do comparative mapping using both a high resolution bathymetry and the broad scale GEBCO bathymetry. And that can be used to fill in the gaps, and we're supplying this to the authorities which manage the marine protected area. I mean, as you'd expect, there's differences in what can be resolved, but between the two different data sets. But it's just to demonstrate that comparable mapping approaches can be adopted regardless of data resolution and are supplied to stakeholders to allow options and flexibility in future decision-making processes and stuff. So just to sort of quickly round off the South Sandwich Trench there. So something I haven't sort of mentioned here, I'm a geologist rather than a biologist, but the discrete basins, for example, I've mentioned before that they're important in terms of connectivity studies for endemic species, but the images in the bottom left there, so we can see some examples of the hadal fauna we observed in our South Sandwich Trench expedition. So we also recorded images of sponges, crinoids, ophiuroids, gastropods and such like. But the top photo there shows two new species of snailfish from 6,000 meters water depth. And these images represent the first findings of hadal fish in Antarctica. And the bottom left, that's a specimen of the amphipod bathycalosoma. That's from 7,400 meters water depth. And this species is endemic to hadal depths and seems to be present in nearly all hadal trenches. But that's useful because that makes genetic connectivity between populations a sort of pertinent question to be resolved using those specimens. Bottom right, that's a specimen of Eurythenes from 7,099 meters water depth. Eurythenes is, so I've been told anyway, characteristically an abyssal family with a complex and cryptic taxonomy at species level. So they usually inhabit upper depths of hadal trenches, but for reasons yet to be resolved, all images and physical specimens acquired. Oh, hang on. Yeah, they occasionally inhabit the upper depths of hadal trenches. So there's a lot of questions about those sort of species that are ongoing just now. So moving on to our next example today, just quickly take you to the Java Trench, so an awful lot warmer than the Southern Ocean. The total area we surveyed was just short of 40,000 kilometres, of which almost 13,000 was new coverage of multibeam data. The deepest point was right in the middle, where the little box C is, and the deepest point is 7,187 meters. But the mean depth of the trench, this part of the Java Trench, is 6,575 meters. As well as the multibeam mapping, we had a dedicated science dive in the submarine, which explored an escarpment on the, it's underriding plate. I've written overriding, but that's underriding. And we also had 7 scientific lander deployments in the Java Trench. So the topography, I mean, I think Java Trench is maybe one of my favourite trenches. I mean, it's just fantastic. Just to sort of take a closer look at some of these areas, a number of seamounts were documented during our survey. Seamounts are known to be hotspots of biodiversity, and the subduction of seamounts and their debris aprons are they're interesting to observe when you're considering sort of the bigger sort of subduction process, potentially influences deformation within the subduction zone. Seamounts are certainly some of the most conspicuous features, but if we sort of take a little zoom in, we can start to see some more subtle indications of this dynamic environment. Once you get your eye, you can start to pick out submarine landslide scars and head walls. You can see more just on this seamount here as well. You can see these little bites taken out the side of the seamount. And these will be these sort of submarine landslides will be triggered either just through loading and gravity, or they might be triggered by earthquakes. This is a region that's gained, a lot of coverage due to, a number of devastating tsunamis in this region. It's important to note that not all landslides produce tsunamis, just like not every earthquake does. But these data give us an opportunity to study whether any of the past landslides had the potential to have generated tsunamis in the geological past. And there's a lot of questions we need to sort of follow on from that initial study. Just to sort of highlight some of the spectacular morphology, again, a bit like a number of other trenches, including the South Sandwich Trench that I showed earlier, we get a number of these faults, which are really pervasive throughout the trench, but have the ability to sort of cut up and chop up features like seamounts, which you might have in your mind's eye that are fairly robust features. But using the techniques such as the ones I described previously for the South Sandwich and ones that are just available in ArcGIS Toolbox, you can start to employ a number of sort of techniques to produce maps of these sort of large data sets, such as the Java Trench. We can accurately map the axis of the trench, faults, seamounts. In this example here, you can see the faulting that's cutting up that seamount is really obviously picked up by this aspect map. And in homage to the broad scale work that I described earlier in the Northwest Pacific, you can start to unpick connectivity, not only within large geographic areas like in that study, but you can actually look at connectivity within a single trench area. And in the Java Trench, we can see, using some fairly sort of rudimentary techniques in a GIS environment, we can identify sort of 7 discrete sort of hadal zones, which has got some interest. It raises an interesting question for biologists that we're working with, looking at connectivity. And there's a few, there's a recent study from the East Indian Ocean, which I've cited there in the bottom there, from Johanna Weston, looking at connectivity of hadal species in the East Indian Ocean, and sort of studies looking at sort of intra-trench connectivity can help shed a bit more light on studies such as those. So I realise that time is wearing on, but this is just a quick overview to sort of show the morphology of the Java Trench. But if we just sort of take a slide just to focus in on that red circle, this is the location of the near vertical fault that we undertook a scientific dive up. And we went from the deepest point in the trench axis, where we saw a lot of fine-grained sediments, and we had the opportunity to go up a sort of 150-metre high fault scarp with talus and sort of rocks, block failures dominating at the base of the scarp. We had bedrock cropping out at seabed, both massive sort of more sort of oceanic crust and basaltic composition bedrock, but also sedimentary bedrock at the top of the scarp. But we also had overhangs, and that's a little snapshot image from the video data in the bottom left there of one of the sort of overhangs that we came across in the submarine. And you can see a number of sort of sponges sort of taking advantage of that outcrop to make their home. Oh, wrong way. There's a lot of seafloor imagery here, but just sort of highlight that a lot of the sort of fabric of the bedrock was being used as fluid conduits. And on the back of that, we had evidence of potentially extensive chemosynthetic bacterial mats, which are existing off the fluids that are erupting from that network of fractures within and bedding within the bedrock face itself. For the biologists in the room, the sort of images on the right-hand side there, I won't go through it all, but it was the Java Trench that the deepest octopus was imaged in during the 5 deeps there at 6,948 meters. We had a stalked ascidian, which is a little image T there, which is normally sort of anchored to the seafloor, but for reasons unknown, it actually come loose and it floated right in front of the camera on the scientific lander. But yeah, really, really interesting suite of papers that we're writing up. And just to finish up, just with one last study that's just been published, inevitably during the 5 deeps, we did find trash. We just had this paper published last month, and it was more a sort of commentary that, you know, there's some exploration vehicles that are being used in Challenger Deep, for example, that are introducing vast quantities of single-use plastic coated tether that have been discarded in these areas. But I mean, it's getting to the stage now that, you know, there's hundreds of meters of yellow and white tether strewn all across the seafloor, and due to its composition, these fibre optic tethers they'll persist in the environment. But not only that, they perform a risk now to equipment. You know, unmanned or manned craft could potentially become entangled in these. So I mean, we're really at a stage now that, you know, the site of the first iconic descent to the deepest place on Earth in 1959-60, you know, is it going to continue to be a safe place that we can explore if the practice of discarding these sort of tethers continues? So yeah, just in case you were wondering what it's like to be in a submarine, I did actually have a really brief chance to get a dive in. I went to the Arctic Ocean and managed to do a dive, lucky enough to do a dive on a seamount in the Arctic at about 2,500 meters water depth. So you get all dressed up in a sort of flame retardant boiler suit. One size doesn't fit anyone. We had a documentary team on board, so you had to sort of stand and talk to the documentary team about your feelings, your loves, your hates, what you're expecting to see down there, and such like. Pause for your photo opportunity, but it was just amazing. You climb into the submarine, get all settled in. The vessel gives sort of last minute safety checks. You are cast adrift and you sink to the seafloor. And the moment where you see the seafloor sort of emerging out of the darkness is just one of those experiences that that'll take forever. Yeah, it's just fantastic. And we saw an abundance of life down there, sea lilies, crinoids, sponges, fish, shrimp. It was just fantastic, and I don't think the smile stopped for about a week afterwards. And then at the end of the dive, you release your weight, you come back up to the surface, and the most expensive Uber ever comes and picks you up. So just, you know, to sort of finish up, you know, understanding more about the deep oceans, some of the most remote and inaccessible habitats on Earth, is crucial for a number of reasons, from regulation of global climate to better understanding of biogeochemical cycles to insights into geohazards, earthquakes, providing baseline data as sort of human exploration for raw materials ventures into ever deeper waters. You know, it's something that we should absolutely invest time, effort, and research funding into. And just as a little aside, that without MASTS and, you know, the relationships and networks within Scotland, I would never have got into all of this Hadal and trench work. I met Alan Jamieson, who was at Aberdeen University at that time, through the MASTS Deep Sea Forum. We had a collaboration going with the members of that forum, Bhavani Narayanaswamy from SAMS, Francis Neat, who was then at Marine Scotland Science. We started off collaborating in the North Atlantic, and before I knew it, I was in trenches all over the world. So I just wanted to highlight there that the MASTS network has led to some of the most sort of formative and exciting work in my career. So my advice for any sort of, well, not only early career researchers, but established researchers as well, is to take part in MASTS and to have conversations and to develop the network, as they can lead to some really different research areas very different to what you maybe imagined your career was going to do. So thanks very much, and I'll finish there.
Excellent. Thank you so much, Heather, for a really visual talk, and also for a really nice positive review of MASTS. So we're very happy about that. And I can't even begin to fathom like how big some of these trenches are. Like, I think that's something that's just super interesting. Just thinking about how big some of the space actually is. And for all our attendees who are with us, if you have a question for Heather, then please pop it in the Q&A box that is at the bottom of your screen. If you're joining us on YouTube, then please use the live chat to submit your question. We've already got some questions coming in on the Q&A, so that's fantastic. And for anyone who's with us who has to quickly nip off but has submitted a question, don't worry, we are going to work through those questions. This session is being recorded, so you'll be able to find the recording on the MASTS YouTube channel later today. And Heather's contact details are on the screen right now if you want to start up a conversation, or just follow her on Twitter as well. So we're going to delve straight into the first question, which is from Andrew, and they are asking how much of the multi-beam data is available publicly. This relates something to, right at the beginning of your talk that I think you were talking about, Heather. Andrew is a part of a team that is starting to pull water column biology from geophys data, and they would like to expand.
Yep, so all of the multi-beam data is, well, from the 5 deeps specifically, is currently openly available on the BGS website, just through the Marine Geo Index and stuff. I can send you some links as part of the Geoscience Data Journal article. All of the links are in that, so I'll certainly be putting that out on Twitter, hopefully within the next couple of days. So all of that data is available. There have been subsequent missions to the Ring of Fire and other areas, and all of that geophysical data at some point will be uploaded. There's an awful lot of it to the BGS website, but it's also been submitted to Seabed 2030, and again, it's all open access. Frequency of EM124, oh gosh, I think the nominal frequency of 12 kilohertz. I'd need to check the paper, but I think that's what the frequency of the EM system that we were using was operating at.
Okay, so thank you for that. Was our second. That was Andrew's second question, was the frequency of the EM124, but you've just answered that, so that's fantastic. We're going to move on to our next question, which is asking, in your Global Ocean 5 Points tour, were you open to adding the Atacama Trench? I'm not sure where that is, so you might have to elaborate.
Yeah, so the Atacama Trench, that's a great question, is also known as the Peru-Chile Trench. So it's off the western coast of South America. I didn't have time to touch upon all of the trenches, but we went to the Atacama Trench. We went in a huge collaborative European funded project called Hades, which is led by Ronnie Gludd, who was at SAMS for a long time, and he has got a Hadel Research Centre based at the University of Southern Denmark now. And so I was along on that trip in 2018, so all of that information is currently being written up frantically, I must add, right now. And yes, so we have been to the Atacama Trench. There are a couple of studies that have already been published by our German partners there as well, and we've just had a paper out in Nature Comms, which was looking at diagenesis in the Atacama and the Kermadec Trench as well. So the papers are coming thick and fast right now.
I'm not sure, is there a kind of collective space where all these papers from your partners, one could find what these papers as they're getting come from, or is it kind of like actually keep an eye on different people's Google Scholars and ResearchGates, do you think?
I'll need to check. So the Hadel Research Centre in the University of Southern Denmark is relatively new, so I think they're still getting their website up and running. On my OrcID thing and ResearchGate, you'll see a number of papers in there. I've got a sort of Hadel Trench and deep water area sort of project on my ResearchGate area. So a lot of the papers I sort of fire into there. Ones where I'm not a co-author on, you know, I usually have liked or commented. But if you're interested, drop me an email and I can certainly give you a little short list of papers that are interesting to read, not only written by me, but by other people as well.
No, and it sounds like you've got quite a lot coming through, you and your partners too. So I very much watch this space with regards to all this work. We're going to move on to the next question that has come in through the Q&A on Zoom. So this person is asking, would you expect to find seeps or vents in these trenches? Have you found any evidence of that? So I don't know I can assume what a vent is, but I'm not sure what a seep is.
Yeah, gosh, I suppose a seep is a slightly more diffuse system. A vent, you might expect to start seeing sort of edifices and structures. I suppose there's probably a bit more to it, but for the purposes of this. Yes and yes to all of that. So I showed some pictures with the really bright oranges and yellows and whites and blues even as well. So those are all seep related, because there's a diffuse sort of a diffuse sort of percolation of fluids up through the seafloor that is being utilised by bacteria in this case, but can be other organisms as well, as a source of energy and food. So they're completely separate from sort of photosynthesis and organic matter raining down from the sky, or scavenging sort of things that fall into the seafloor. They think the deepest known vent system is the Shinkai seep field, and that is in the Mariana Trench at, I think, just shy of 6,000 meters, like 5,960 meters or so. We have found some other evidence of vents that we're currently trying to write up just now, but I mean, it's super exciting and interesting. And again, some of the relic vents that we sort of completely serendipitously found, again, that's in the Mariana, but unlike the Shinkai seep field, which is on the sort of forearcs, the overriding plate, the one that we've sort of tentatively found is on the underriding plate. So still just doing a little bit of reading around the subject to see kind of how relevant its sort of geological position maybe is to the entire system.
Oh, that sounds really interesting. Great. We're going to move on to Matt's question, and they are asking, has seismic tomography been applied on the South Sandwich Trench? And love that name.
That is a great question. So actually, have you been reading my emails? I've just had an email from some guys that I know at MARUM in Germany, and they have some students, some PhD students, who are looking at the some of the larger scale sort of global processes in the South Sandwich Trench. So I don't know specifically if any seismic tomography has been done as yet, but I'm just having conversations now. I'm going to be supplying data to these collaborators at MARUM, and I'm going to be setting up a meeting to chat to them in a couple of weeks' time. So maybe in a couple of weeks' time, I'll have more information.
Understood. We're going to move on to Andrew's question, which kind of relates to something you touched upon at the end of your talk. You mentioned plastic tethers littering the deep, but what about the weights that the machines and the submersibles that you've been involved in? What happens to them?
Yep. Yeah, so I get asked that quite a lot, actually. Yeah, and I think that's a very valid question. The weights that we use are, I mean, they're just sort of iron, metal, and they rust really quickly, actually, in the deep sea, in the saline environment. And they're also, it's not like we've got sort of weights that are the size of cars or anything. I mean, it's kind of, maybe the size of a old-fashioned computer monitor, one of the big sort of fat, deep ones. They're relatively small, and even the ballast weights for the submarine, they're sort of long, sort of tubular, or maybe a meter long or something. So the environmental impact from dropping these is relatively small compared to some of the other things that we have seen in the environment, and also some of the other things like the plastic tethers that I highlighted there. They're going to persist long term, whereas the metal weights and stuff, I mean, I don't know the exact sort of residence time of them, but they do disappear. They just rust down. They're like iron ships that sunk. They just eventually just become rusticles and then just dissolve away.
Okay, thank you. We're going to move on to Tim's question. and they are asking, is the available data the raw data or grids? The backscatter imagery will be very useful, or have you done that already?
Yeah, so I mentioned earlier with one of the other questions that everything's open access. It is coming in sort of stages, so a big bunch has gone online. We've got it submitted to Seabed 2030 as well. It's all submitted to NOAA, so we've kind of scattergunned everything. It's all the exact same version, exact same processing and stuff, you know, but it just means that we're just trying to make sure that we hit as wide an audience as possible. We do have backscatter data as well. It does vary, you know, I mean, Tim Lebat, you know, he is an expert in backscatter intensity data and processing from from Southampton and Knock down there. Yeah, we do have the backscatter. It's a variable quality, you know, function of water depth and weather, as Tim knows all about. But yeah, we have that, and we have been using that in our mapping and research. And again, it will be available.
Yeah. The next question isn't really a question, but it's a comment which I think many of us can relate to, in that very impressive that you got to go into the submersible and how you coped with such a claustrophobic kind of space. How does one actually prepare for that? What would you say? What is it like? Do you just hop in and it's quite comfortable?
You just hop in. Yeah, I mean, actually I get asked this quite a lot. I was always surprised because I'm not trying to be brave, but I honestly didn't have any reservations about the submersible dive. And I think that's because I had been working and going to sea with these guys for over a year. So I knew them all really well. I knew the person that designed it. I knew the guy that built it. And I knew the guys that were maintaining it. And I had absolute faith in it. I think it's a bit of a personal decision as to whether you can cope with small spaces. So, I mean, I'm okay, but I know that others really aren't. But I mean, it's comfortable. You're in a sort of lovely sort of seat. You can't stand up. So, I mean, your dive cycle, my dive cycle, I think, was only about 7 or 8 hours. But I mean, for a deep dive to the bottom of the Mariana Trench, for example, you're talking like 10 hours, 11 hours. So, you know, you have to think about, well, you know, if I've got a bad back, you know, you're not going to be able to move you know, for that length of time, really, you know. But and it gets cold. That's something to bear in mind. Yeah, you had to make sure that I had a woolly hat and some gloves, because actually the inside of the sphere, you know, even in the warm water, you know, Java Trench, for example, I think the surface water temperature was 28 or 30 degrees, but the bottom temperature is still only like 1 or 2. So, you know, the sphere itself does chill down even with all the electronics on and stuff. So
yeah, it's very interesting. Yeah, and I understand, like, the familiarity, as Phil says, makes it a bit more comfortable, but really a really interesting insight into what it's like to go that deep in water. We have one more question left, so if any of our attendees who are still with us and you have a question that you haven't yet asked, please type it in now so we can work through it. The next question is from Leah. They are asking, they've wondered about safety of submersibles and ROVs in these subduction zones, given the fact that ruptures, earthquakes could be as significant in some of these areas. What do you think about hazards about exploring in such areas now that they are probably being more explored than ever?
Wow, crikey, that's a really good question. I suppose there's an aspect of trying to quantify how frequent some of these hazards occur, you know, and that's a huge, you know, body of work, and you know, it's a big question that's still being answered. I think sort of personally, as a sort of personal opinion, you know, sending ROVs and submersibles into some of these areas, as long as all of the, you know, risk assessments and the safety on board the boat, you know, the vessel, the vehicles themselves are well maintained and everything, then, you know, in my opinion, it's no more dangerous than jumping on a bus. You know, it's just, you know, it's great, you know, I mean, and to have access to some of these research facilities is amazing. Yeah, it's a really great opportunity. Yeah, I mean, the 5 Deeps expedition has been part of a 5-part documentary series that has just been broadcast on Discovery Plus, their new streaming service. So that only came out last week or something, yeah, 1st of April. So go and have a look. Don't judge me too hard. It was all done very sort of, you know, for TV. But my point is that they were constantly asking, they were looking for the danger element, and it just isn't there. I mean, the likelihood that, a submersible or the lander would be somewhere that a submarine landslide would come and wipe it out are so small. I mean, if you started thinking about some of these things, then, you wouldn't necessarily leave your house ever. So, yeah.
That's really interesting. And that's all our questions that have come in from our audience. So that leaves me to say thank you very much, Heather, again, for being today's MASTS webinar speaker. And for anyone who wants to follow up with Heather, her email is on the screen and her Twitter handle is there as well. So make sure to drop her a follow if you aren't already. Thank you very much, Heather.
Thank you very much for having me.
If you're still with us and you liked what you heard today and you want to find out more about other topics that regard marine science, then please check out maybe next week's MASTS webinar, who is going to be Dan Goldberg from the University of Edinburgh. But we are actually running until the end of May. So maybe one of these other talks is something that you're interested in. All you need to do is head to the MASTS website and find the sign up link on the upcoming events page, and you'll be able to sign up for any of these other talks that are happening. We look forward, we hope that you can see us, join us again, and I hope you enjoyed today's MASTS webinar.